So let us continue the discussion of the evolution of the basis operators when we will consider various kinds of pulse sequences. So we have to know how the individual basis operators evolve under the influence of different Hamiltonians. Basically there are two components of the Hamiltonian we are dealing with, and there will be a Zeeman Hamiltonian and the coupling Hamiltonian. And last class we looked at the evolution of a particular base operator IKX under the influence of the chemical shift Hamiltonian. Today we will discuss the evolution of that same operator IKX under the influence of the scalar coupling Hamiltonian. So to remind you as to what is the scalar coupling Hamiltonian, let me just write here, the scalar coupling Hamiltonian is written as Hj is equal to 2 pi jkl, jkl is the coupling constant between two spins k and l, and we have these operators ikz, ilz. So this is the, for the two spin case, this is the coupling Hamiltonian. So for the evolution what we need to calculate is we have to calculate e to the minus I hj t, and we using the same basis operators, this will be e to the I hj t. And if I explicitly write this here, so I have this bs double prime, this is the operator that we get as a result of the evolution. Here you have e to the minus I 2 pi jkl ikz ilz t ikx e to the I 2 pi jkl ikz ilz t. Now this individual operator can be expanded or written in a simpler form like this: e to the minus I 2 pi jkl ikz ilz is equal to cosine pi jkl t by 2 minus 4I sin pi jkl t by 2 ikz ilz. This can be proved along the same lines as we derived the expressions for e to the I bx, for example. When we took the expression for e to the, let me write here, so we will write here e to the minus I beta I k I z. So we wrote in a particular manner here cosine beta by 2 minus I sin beta by 2 and things like that. So this was x here. If you are applying it for the pulse, this was x here, e beta is a flip angle, then we wrote is equal to cosine beta by 2 minus 2I sin beta by 2 Ix. So that was how it was written. So in the same manner we write this here, except we make note of the fact that Ikz Ilz can be written as, in terms of the polyspin matrices, 1 by 4 sigma Kz sigma Lz. So this will help us in deriving this equation. Okay, and polyspin matrices satisfy this condition, their sigma z square is equal to sigma Lz square is equal to 1. So this is the property which we should remember, and we can prove this equation. So therefore I am not going to explicitly prove this. This can be a kind of an exercise for the students who can practice this and prove this equation. So we will actually use this equation now as it is and calculate the evolution of the kx operator under the influence of this. So in this place we will have to put this, and on this place what we should do, Ikx, and this will be a plus sign. When you write for I2 pi jkl ikz ilz t, then this will be the same as this, except we will have a plus sign here for I sign, and then you do the multiplication of this part Ikx and the other part which is with the plus sign, then you arrive at this equation Ikx cosine pi jkl t plus 2 iky ilz sin pi jkl t. So this will be the kind of equation that will come. You notice here that Ikx has evolved into a in phase Ikx term, and it has generated what we may call as your antiphase term. It is the K magnetization which is antiphase with respect to the spin L. You remember earlier we have discussed what these individual basis operators represent. Therefore here we have said under the influence of the coupling Hamiltonian, the Ikx operator will evolve into this ikx cosine pi jklt plus 2 iky ilz sin pi jklt. So, this is the antiphase term. So, such evolutions will keep happening, and we will look at them as we go along. Now, similarly you can calculate for the basis operator iky evolution under the Zeeman Hamiltonian, this is the chemical shift Hamiltonian, and the coupling Hamiltonian Hj, and they can be represented in this manner. We will not prove this, basically they can be derived in the same manner, and we will just write it down here and we can use them later. So, the Bs prime will be cosine omega kt iky, this is for the k spin, here for the single spin, and we have minus sine omega kt ikx. So, because here we have considered the evolution of the kx operator. So, the ky operator evolves with the iky here and minus sine omega kt ikx. Similarly, the coupling Hamiltonian generates this sort of the evolution, the Bs double prime iky cosine pi jklt minus 2 ikx ilz sin pi jklt. I want to point out here one thing, that when you are actually calculating ikx, remember we had ikx here in this term, but plus 2 iky ilz. Now here you see, if you are starting with iky, this gives you iky cosine pi jklt minus 2 ikx ilz. Similarly, in this case also, when you had ikx evolution, it was ikx cosine omega kt plus iky sin omega kt. If you are considering iky, then it is iky cosine omega kt minus sin omega kt ikx. Therefore, this indicates in some way a kind of a rotation in the transverse plane, and we can pictorially represent them very soon. I already indicated this to you in the chemical shift evolutions earlier, that such kind of a representation can be used for calculating the evolutions of any of these operators, whether it is iky or ikx or minus iky, minus ikx and things like that. Now, similarly we can do this exercise for the basis operator 2 ikx ilz evolution under hz and hj. Now, hz works on individual spins, therefore, if I consider 2 ikx ilz, though which is the transverse term here, the transverse term is ikx. Therefore, chemical shift evolution will happen only for the ikx part. ILZ part will not contribute to the chemical shift evolution. Therefore, if I consider the Bs prime here, so this will be simply 2, and ikx term evolves as in the case as indicated here earlier, ikx cosine omega kt plus iky sin omega kt, and ILZ remains as it is, there is no change. So, even if it is in this form, the two product operator, the chemical shift evolution works on the individual operator, because we have the ILZ here and we have the ILZ coming here. IKX evolves in the usual way as it is for the individual single spin. Now, the coupling Hamiltonian causes this sort of a transformation here. It gives you cosine pi jklt 2 ikx ilz. So, the antiphase term which remains, it is amplitude modulated by this expression cosine pi jklt, and you generate here iky plus sin pi jklt. Notice here that when you considered iky rotation, you got iky cosine pi jklt minus 2 ikx ilz sin pi jklt. Now we are considering this, you are generating the same terms once more. So this appears in the positive sign, then you have plus sin pi jklt iky. So this indicates to you that these kind of terms form some sort of a group, they transform within themselves. The Hamiltonian here is ikz ilz, and the operator is ikx il, the basis operator is 2 ikx ilz, and we have also another basis operator 2 iky. So 2 ikz ilz, 2 ikx ilz and iky, they somehow form a kind of a group, and similarly for the ikx as well. This can be represented in a pictorial manner like this. So similarly I can write the same kind of expressions for 2 iky ilz under the influence of hz and hj. So Bs prime here gives me the same here evolution of IKY as the individual chemical shift evolution, and ILZ remains here. And Bs double prime, which is the result of evolution under the coupling, you get cosine pi jklt 2 IKY ILZ same here, and it generates the IKX term. So as I said, these indicate some sort of rotations in a particular plane. Pictorially we can represent it in like this. So we put the Hamiltonian, this is for the coupling, similar thing we wrote earlier for the chemical shift. So the coupling, the Hamiltonian is written along this axis here. So IKZ ILZ, this is the coupling Hamiltonian, and if I take the particular base operator IKX here, then it under the influence of this rotation, evolution under this circle indicates the evolution under this Hamiltonian, it rotates in this manner. So you get when it rotates like this, you generate components of IKX and 2 IKY ILZ. Suppose it has rotated up till here, then you generate IKX cosine pi jkl tau and a sine IKY ILZ sine pi jkl tau. And if we were to continue this rotation under the influence of the same Hamiltonian like this, so what you will get, though this vector has moved over here, so you get 2 IKY ILZ cosine pi jkl tau as it is here. Suppose it has moved until this, if I want to draw a vector as well here, if I wish to draw a vector here, so then if this rotation has happened for a particular angle, this angle, and this will be the pi jkl tau, and you will write the cosine pi jkl tau. So if this is pi jkl tau here, then you will have the 2 IKY ILZ cosine pi jkl tau, and this component will be minus IKX sine pi jkl tau, right. So and similarly it will continue this. If you were to start here, you will move here, if you were to start here, you will move here, and things like that. Therefore these actually transform within themselves. This IKX, 2 IKY ILZ and IKZ ILZ, this form a group with transform within themselves. Go from here to here, you get this, from here to here you get this, and you can go from here to here, again you get this and this under the influence of the same Hamiltonian. So if I were to write here in the similar manner here to IKX ILZ, so I get here IKX going to IKY and IKY going to minus 2 IKX ILZ here, and so and this continues to generate me this portion here and the minus IKY here, so like that. So this whole set of operators which are present here to IKX ILZ, IKY and this coupling operator here, this to IKZ ILZ, these form kind of a rotation group. When I say rotation group, they transform within themselves. So under the influence of one thing, the one operator transforms into the other. So that is the meaning of the rotation group. So this is these are very useful expressions for calculating the evolution of any density operator as we get along. Okay. Now that is so much for the evolution of the basis operators. So those are illustrative examples which I gave you, but there will be, we have to do this exercise for every other rotation the basis operator. This can be easily done because we already indicated what sort of principles are involved, what sort of rotation groups are formed, and therefore it is easier to write down the expressions for all of those. Now we turn to the evolution under the influence of pulses. What do the pulses do? And we have seen earlier the particular basis operator gets transformed by this sort of a transformation. If this represents a rotation, this represents a pulse here, and this is the basis operator, this is again a pulse p, ps, p minus 1, and the pulse can be applied along the x or the y axis, and therefore I write here rq, the rotation operator rq, and rq minus 1. So these represent the pulses. Q can be x or y. Now let us actually calculate the influence of this on some basis operators. We take as an illustration Bs is equal to Iz. This is the simplest all of those, and for a 90° x pulse the transformation will be, we have to write the individual matrices for these pulses. So we have here Rs, suppose we apply it along the x axis, we have said 90x pulse, therefore this is Rx pi by 2 Iz Rx minus 1 pi pi by 2. And we have derived earlier what this Rx pi by 2 is in terms of a matrix. So this will be 1 over root 2 1 minus I 1, and then for the Iz we have this representation 1 by 2 1 0 0 minus 1. This is the matrix because a single spin, we are considering a single spin here, and Rx minus 1 pi by 2 will be the inverse of this matrix. So this will be 1 by root 2 and that is 1 I 1, right. So one can calculate the inverse of this. If you may take a product of this matrix and this matrix, you will get 1, right. So that indicates that this is the inverse of this. Now when you do all these multiplications, you will get 1 by 2 0 I minus I 0, and this is equal to minus Iy, right. So what this has told us, that 90-degree X pulse rotates the Iz into minus Iy, right. So this is also what we had said earlier in the discussion with the derivation of the pulses, and that was, we can write is so this is the x, y, z, and if I have a vector here Iz operator, this gets transformed into minus y. So it goes here x, y, z, it goes into minus y, gets rotated here to minus Iy, Iz goes to minus Iy if I apply a pulse along the x axis. Okay. So that is the calculation what we got from this 90-degree X pulse. So Iz operator 90x, this is indicated here in the figure. So actually, so this figure is already there. So if I write here rotation around x and this is y and this is the z, so the rotation operator is along this Ix, and z magnetization is rotated into the minus Iy. So from the same we could also see what if your magnetization was along the minus z axis, it will go to y. If it were along the y axis, it will go to plus z. So if you are considering this initial operator here as Iy, then you can imagine that this Iy will go to Iz. We said Iz will come to minus Iy. This is what we had in the explicit calculation. Now if we were to start with Iy, the same rotation will take Iy to Iz, okay, and Ix will of course be invariant, nothing will happen, we will explicitly show that also, and if we were to have minus Iy, then minus Iy will go to minus Iz under the influence of this rotation. Okay. Now that is explicitly calculated here. If Bs is equal to Iy, then what I have to say here, Rx pi by 2, Iy Rx minus 1 pi by 2. Now I put the same matrices here, 1 by root 2, 1 minus I 1, this is half, this is the Iy operator, half 0 minus I 0, and this is 1 by root 2 1 I 1. This is the inverse of this matrix, and if you calculate this, you get half 1 0 0 minus 1, that is Iz. So this is the same which I told you before, that under the same rotation the Iy is going to Iz. So therefore these again form a rotation groups, x, y and z, these form rotation groups, they transform within themselves. If there is a change in sign, of course that is not considered different, it is the same rotation group, just except that the coefficient will be different. So this rotates y into z, rotates z into minus y, and z rotates minus y into minus z, and so on. So this forms a rotation group. You remember, if I had my the rotation around the z axis, rotation around the z axis was what? That is the chemical shift evolution. When I had the chemical shift evolution, my operator was going from here to here, Ix was going to, part of it was rotating in this plane, x to y, y to minus x to minus y, and so on and so forth. Therefore these three operators form a rotation group, and one of them can be the basis operator, other one can be your Hamiltonian. In this case the operator is the Ix, the rotation is around this axis, therefore, and we have the basis operator is Iz or Iy. In the chemical shift case, this was the Hamiltonian, this was the operator, and the basis operators were here, and therefore one could go from Ix to Iy to minus Ix and so on and so forth. So this is the way we can look at all of this in a comprehensive manner. So this Iy goes to Iz. So for a Y pulse, earlier I wrote as X pulse. So what does the Y pulse do? So the Y pulse take this rotation here, you can do the same calculation. So it goes Iz goes to Ix. Notice you have a left handed rotation here. Iz goes to Ix and Ix will go to minus Iz and minus Iz will go to minus Ix and so on. So this is the way we describe the rotation groups, rotation under the influence of the various pulses. Now what about Ix itself? Suppose your base operator is Ix and I apply 90° X pulse. Intuitively you would think that okay, nothing should happen to it, but let us also prove it. So we put Rx pi by 2, Ix Rx minus 1 pi by 2. So I put the same matrices here, 1 by root 2 1 minus I 1, half 0 1 1 0, 1 by root 2 1 I 1, and this will give me half 0 1 1 0, and this is Ix. So therefore the Ix is invariant under Rx pulse. So that is intuitively one would have imagined that you have put the magnetization along the same axis and you are applying a rotation around that axis and it should not move in principle. Now let us consider multi-spin basis operators. So far we looked at the individual spin operators and we now turn to multi-spin operators. The effects of pulses can be applied on individual spins. Now the pulses can be applied on all the spins or on individual spins. So the effects will be different. Now here we consider a basis operator 2ikx ilz, and we have seen this operator represents the K magnetization which is antiphase with respect to L, and this is a single quantum coherence because this is Kx, okay. Kx Lz is a single quantum coherence, X magnetization of K antiphase with respect to L. Now we apply a pulse on both the spins 90xk plus 90xl. So this is called as a non-selective pulse, it is applied to both the spins K and L. So now what happens when I apply Kx pulse, nothing happens to Kx, right, because we said this is invariant, X magnetization is invariant under the X pulse, therefore nothing happens to the Kx operator. And what happens to Lz? Now Lz goes to minus Ly, this is we calculated, Z goes to minus Y, right. So therefore X pulse on L spin take this ILZ to minus ILY, therefore I get here minus 2ikx ILY. So what is this? Now here we got a mixture of double quantum and zero quantum coherences. This we have explicitly calculated earlier that this represents a mixture of double quantum and zero quantum coherences. So what we have done here is by applying a non-selective 90° pulse on antiphase magnetization of one spin, we have converted that into a mixture of double quantum and zero quantum coherences. So these are called as coherence transfers, and various kinds of experiments will make use of such kind of transformations. Suppose I take the same operator here, now I apply a pulse, not 90x pulse, but I apply a 90y pulse, anti-y pulse on both the spins. So if I take x, what happens to x? So you have to recall when I apply a y pulse, what happens to x? So and 90y on Lz will take me to 90 Lx, and this will take me to minus 2ikz. So you have to go back and look at what happens when I apply a y pulse on X magnetization. Let us go back and look at this. So this will be easier to follow if you do that. So looking at here, so what happens when I apply y pulse on X magnetization, it will go to minus z, right, and y pulse on z will take me to x, correct. So therefore this apply them here, so I get this will go to minus z and Lz goes to Lx, therefore I get here minus 2ikz Ilx. Now notice here just the phase change of the pulse has made a huge difference in the transformation. This was antiphase magnetization of the K spin with respect to spin L, and now what we have here, this is X magnetization of L spin antiphase with respect to the K spin. Now this is a single quantum coherence, this was single quantum, this was single quantum, this is also single quantum. When we applied an anti-X pulse, we had got double quantum plus 0 quantum here from this basis operator. Now when you apply a Y pulse to the same basis operator, I get a single quantum coherence of the L spin. So this is a different kind of a coherence transfer, single quantum to single quantum from one spin to another spin which are coupled. From K spin to L spin I get a transfer, and this is a single quantum to single quantum coherence just by changing the phase of this 90-degree pulse. So in the earlier case, when the 90-degree pulse was along the Y axis applied to both the spins, so I got a single quantum coherence into a mixture of double quantum and 0 quantum coherences, and so this has important implications. So this represents conversion of antiphase X magnetization of K spin into antiphase X magnetization of L spin, that is a single quantum coherence transferred. Now suppose we apply once again with the same operator, base operator here, but I apply a pulse only on the K spin for example. I will not apply along the L spin at all. That means I apply a selective pulse, a selective 90-degree pulse on one spin only. I apply to only the K spin. So therefore the L spin remains unaffected because I have not applied any pulse onto that, and Kx takes me to the minus Kz. Therefore this will go 2ikx ILz takes me to minus 2ikz ILz. So it is a completely different transformation once more. Now this antiphase magnetization has now got transformed into ZZ order. ZZ order has to do with the order of the populations in the two states on the top, alpha alpha state and the beta beta states, as we had discussed earlier. So this antiphase magnetization of the K spin is getting transformed into ZZ order. Simply by changing what kind of pulses we apply, we get different kinds of transformations of the basis operators. So now if I apply on the other hand the same basis operator once more here, but I apply a pulse, selective pulse only on the L spin, not on the K spin. Earlier when I applied on the K spin, I got ZZ order. So now I apply it only on the Y spin. So what I get here, Kx remains Kx because no pulse applied, and Lz takes me to Lx, to Ikx Ilx. Now this is a mixture of double quantum and 0 quantum coherences. Okay. So therefore you see once again how a single quantum is converted into double quantum plus 0 quantum coherence by changing the kinds of pulses we apply. So you notice therefore that a combination of different kinds of pulses with the different cases can really be used to create a whole lot of transformations in your density operator, and all of these one we will use when we actually calculate various pulse sequences, and that will become an important. But this will be easy to calculate in a simple operator form, product operator form. So similarly here 2iky ILz, so far I was looking at 2ikx ILz, and we can calculate similarly for 2iky ILz. If I start with 2iky ILz, apply a non-selective pulse on x, both k and l spins along the x axis, then I get this into 2ikz ILy, and this is now the L magnetization antiphase with respect to k. This was K magnetization antiphase with respect to L, and this is L magnetization antiphase with respect to P. So single quantum to single quantum coherence transfer. So these are important results which will play a very major role in how we calculate the evolution of the density operator through the pulse sequences. So this is referred to as coherence transfer from spin K to spin L. In general, it is seen that application of RF pulses to antiphase magnetization in multi-spin systems causes coherence transfer among the spins is from the basis of many multipulse experiments in homo and heteronuclear multi-spin systems. So here is a summary of all of these evolutions what I have indicated here once again as a recap. So because this will be extremely useful and we have to remember this very well, we have to remember this by heart, which operator turns which basis operator into what. So which Hamiltonian converts what basis operator into what basis operator. So we will have to see all of this. So if this is chemical shift evolution, your Hamiltonian has the IZ operator here, therefore we write in this manner, and your basis operators are Ix and Iy. Therefore, Ix rotates into the Iy and Iy rotates into minus Ix rotates into minus Iy, and so on and so forth. So, all transformations happen here. These form a rotation group. These 3 operators form the rotation group. So, scalar coupling evolution, once again the same thing is repeated for the benefit of consolidation. So, you have this the Hamiltonian is 2 ikz ILz, we put it along the z axis. This is my axis. So, this axis is now 2 ikz ILz, and ikx is rotated into mixture of ikx and 2 iky ILz, and the same Hamiltonian rotates the basis operator 2 iky ILz into mixture of 2 iky ILz and minus ikx. So, if I were to start from minus ikx, I will get minus ikx plus the cosine component will be minus ikx, and I will get here minus 2 iky ILz. Now, if I want to put here the anti-phase magnetization, here it was starting with the in-phase magnetization, this is how they transformed. If I start with 2 ikx ILz, this anti-phase magnetization, and this operator remains the same 2 ikz ILz, this rotates into iky. So, this will be the cosine component will be 2 ikx ILz, the sine component will be iky. So, if I consider the rotation further, iky rotates into minus 2 ikx ILz, partly it remains as iky, the cosine pi jkl tau will be iky, and the sine will be minus 2 ikx ILz, minus 2 ikxl sine pi jkl tau. So, this is the way rotation happens. I mean, when you wrote here, this is the rotation is happening depending upon the value of tau, your vector will be somewhere here or here or here, wherever. So, if it is equal to pi by 2 if tau is such that this whole rotation is pi by 2, then you will go entirely from here to here. If it is not pi by 2, if it is the whole thing is equal to 30 degrees or 45 degrees or something, then your vector will be somewhere here. So, you will have a cosine component and a sine component. Similarly, here if you are rotating by an angle pi by 2, that depends upon your value of tau, then this goes completely into this, but if it is less than that, the vector can be somewhere here, then you will have a cosine component here and a sine component. So, with regard to this. So, this is the way we actually calculate the evolutions under the influences of various Hamiltonians. So, about the rotation by pulses, so if I have an x pulse, the Iz rotates into minus Iy. Notice here we consider a 90 degree pulse which goes into this, but you can extend this argument to say, well, I do not want to apply 90 degree pulse, suppose I apply a 45 degree pulse, what happens? In fact, very easy to imagine here. Now we understood the principles how the rotations are happening. If I were to rotate by 45 degrees, then the rotation will take the vector from here to here. So, this angle will be 45 degrees, so I will have a component Iz and a component Iy minus Iy. So, any angle can be chosen. So, if I have a 90 degree pulse, it takes me to minus Iy, but if I have a beta pulse, then I will have cosine beta component for the Iz and the sine beta component for the minus Iy. So, similarly, if I apply this pulse, to the Iy magnetization goes for a 90 degree pulse, it will go here, but suppose I were to apply a pulse which is not 90 degrees, somewhere 45 degrees or something or 30 degrees, then I would rotate it only up till here, then we will have a cosine component here and a sine component here. Similarly, if I were to take a rotation around the y axis, a pulse along the y axis, the rotations will happen like this: Iz goes to Ix, Ix goes to minus Iz takes you to minus Ix, and again minus Ix will take you to Iz. Once again the same arguments apply with regard to the flip angle. Instead of a 90 degree flip angle, if you use a different flip angle, you will get different components along the y and the z axis. So, with that we will stop here and we will continue the discussions in the next class.